Black holes. I mean, just the name itself sounds incredibly mysterious, doesn't it?
It really does. Conjures up images of, well, cosmic voids.
Exactly. These ultimate devourers where gravity just goes off the charts. So strong, even light can't escape. So today, that's where we're headed, deep into these things. And your mission, listeners, if you want a bit of a mental adventure, is basically to get a good, quick grasp of what black holes are and some of the pretty wild cosmological theories around them without getting totally bogged down.
Yeah, we want to avoid that feeling of information overload. We've looked at some really fascinating material on this.
Right. Based on that source doc, sure.
Exactly. And the goal here is to pull out the really key nuggets, the core ideas that make black holes so important in cosmology today.
Making the complex accessible, hopefully.
That's the plan. We'll go from the basics, what is it, all the way to, what they mean for the universe itself.
Okay, let's jump right in then. So, starting simple. What is a black hole, fundamentally?
Okay, so at its heart, it's a region in space-time where the gravitational pull is just overwhelmingly strong.
Overwhelmingly. Like nothing gets out.
Nothing. Once you cross a certain boundary, we call it the event horizon, there's no escape. Not even for light.
Wow. And where does this insane gravity come from? It's not just there.
Right.
No, it's caused by a huge amount of matter being squashed into an incredibly small area.
Squash how small?
Think about taking, say, several times the mass of our sun and compressing it down to maybe the size of a city. The resulting gravity is, well, almost unimaginable. That's, hard to picture. And I hear they're not all cookie-cutter objects. They're different sizes.
That's right. We generally talk about two main types. Stellar mass black holes, maybe a few times the sun's mass.
Okay, relatively small, cosmically speaking.
Relatively. And then you have the supermassive black holes. These are the real giants. Millions, sometimes billions of times the mass of the sun.
Billions. Where do you find those?
Usually right at the centers of most big galaxies, including our own Milky Way.
Okay, that's staggering. Now, this idea, it's not brand new, is it? People have thought about things like this for a while.
That's a good point. The very first hints, mathematically speaking, actually go back to the 18th century, sort of theoretical curiosity.
Really? That far back?
Yeah, but the modern understanding, the real framework, that comes much later with Einstein.
Einstein again, general relativity, 1915.
Exactly. His theory completely changed how we think about gravity.
How so? It wasn't just a force pulling things?
No. He described gravity as a curvature, a warping of space-time itself caused by mass and energy, like putting a bowling ball on a trampoline.
Okay, I get the analogy. So how does that lead to a black hole?
Well, his equations showed that if you concentrate enough mass in one spot, the curvature becomes extreme. So extreme, it basically pinches off, creating this region with infinite curvature, the singularity and the event horizon around it.
Infinite curvature. Okay, so how do these things actually, get made? What's the recipe?
The most common way, we think, is stellar collapse.
From stars dying.
Exactly. Really massive stars. When they run out of fuel, the outward pressure stops and gravity wins. The core collapses catastrophically, a very big boom, a supernova. But if the core left behind is massive enough, maybe more than about 3 times the sun's mass, gravity crushes it completely into a black hole.
Okay, so massive star death is one way. Are there others?
Yep. Another fascinating way is through mergers. You can have 2 neutron stars, incredibly dense stellar remnants themselves orbiting each other.
Right, dense little things.
Very dense. They spiral closer and closer, losing energy as gravitational waves.
Those ripples in space-time.
Precisely. And eventually they collide and merge. If the combined mass is enough, bang, another black hole, or a neutron star merging with an existing black hole can do it too.
Okay, merging dense objects.
Yeah.
I think I read about primordial ones from the early universe.
Ah, yes. Primordial black holes. These are still hypotheticals, mind you.
They're theoretical.
The idea is they didn't form from stars. They might have formed right after the Big Bang, when the universe was incredibly dense and lumpy. Tiny, high-density regions could have just collapsed directly into black holes then.
Huh. Tiny black holes from the dawn of time. Wild. And the big ones. The supermassive ones in galaxy centers. How did they get so huge?
Now that is a major area of research right now. It's a bit of a puzzle.
No single answer yet.
Not definitively. Could be several things working together. Maybe they started smaller and just grew over billions of years, swallowing gas, stars, other black holes.
Like eating everything nearby?
Pretty much. Another idea is that maybe huge clouds of gas in the very early universe collapsed directly into massive black holes. Very, very slowly. It's a mind-bending consequence of combining quantum mechanics and gravity near the horizon.
Wow, okay. So they're much more complex than just holes.
Yeah.
Which leads us nicely into the bigger picture cosmological theories. How does general relativity explain them?
Well, GR is the foundation. Einstein's field equations, which describe how space-time curves actually predict black holes as possible solutions. If you have enough mass in one place, the equations naturally lead to something like a black hole.
So they popped out of his math.
Essentially, yes. The simplest solution is the Schwarzschild solution describes a perfectly spherical, non-rotating, uncharged black hole. Kind of the textbook ideal case.
But real ones probably aren't that simple.
Almost certainly not. Most things in the universe spin. So the Kerr solution is likely more realistic. It describes a rotating black hole. That spin actually drags space-time around with it, which is another weird effect.
Just time drag. Okay.
And there are other solutions too for charged black holes, like Reisner-Nordstrom or Kerr-Newman. But we generally think real black holes wouldn't hold much charge. They'd attract opposite charges and neutralize themselves pretty quickly.
So GR sets this stage. But you mentioned quantum mechanics earlier, and that it causes problems.
Big problems. Or maybe big opportunities. Reconciling general relativity, our theory of the very large, with quantum mechanics, our theory of the very small, is arguably the biggest challenge in fundamental physics today.
The Holy Grail, sort of.
You could say that, and black holes are right at the center of this conflict, particularly with something called the black hole information paradox.
Information paradox. What information gets lost?
Well, think about throwing a book into a black hole. All the information in that book, the words, the story, seems to disappear beyond the event horizon.
Gone forever.
According to classical GR, yes. But a core principle of quantum mechanics is that information can't truly be destroyed. It can get scrambled, hidden, rearranged, but the total amount of information should stay the same.
So GR says it's lost, QM says it can be. That's the paradox.
That's the essence of it. It's a fundamental clash between our two best theories of the universe. Where does the information go? Is it lost, violating quantum mechanics? Or does it somehow get preserved or escape?
Does Hawking radiation help here? Does it carry the information out?
That's one of the big hopes, and a major area of debate. Hawking himself initially thought the information was lost, but later changed his mind. The radiation is thermal, meaning it seems random, carrying very little information classically.
So it doesn't seem to have the book story encoded in it?
Not obviously, no. But perhaps the information is encoded in subtle quantum correlation.
Could be tiny ancient black holes.
It's a possibility. We haven't found them, but people are looking. It's an intriguing idea because they interact gravitationally, just like dark matter seems to, but not through light.
That would be amazing,
right,
if true. And the supermassive ones, what's their cosmic role?
Oh, they're hugely important for galaxy evolution. We now think the growth of a galaxy and the growth of its central supermassive black hole are somehow linked.
They grow together how?
The black hole's gravity obviously influences stars nearby, but also, when it actively feeds on gas, that accretion disk we talked about, it can blast out incredible amounts of energy and radiation, jets, winds.
Powerful outflows.
Extremely powerful. These outflows can push gas out of the galaxy or heat it up, basically regulating or even shutting down star formation across large parts of the galaxy. They help shape the whole structure and evolution.
So they're not just sitting there, they're active players in how galaxies live and die.
Absolutely. Active galactic nuclei, powered by these feeding black holes, are some of the most luminous objects in the universe and have a profound impact.
Okay, now what about the really cutting edge stuff? String theory, holography, how do they fit in?
Right, these are theoretical frameworks trying to dig deeper, potentially unifying gravity and quantum mechanics. String theory, for instance, replaces point particles with tiny, vibrating strings, and it naturally incorporates gravity.
Does it help with black holes?
It offers ways to calculate things like black hole entropy, a measure of their information content that match predictions from other methods, which is promising. And it leads into this even stranger idea, the holographic principle.
A hologram universe idea. Sounds like science fiction.
It does, but it's a serious theoretical concept,
Right.
especially through something called the AD-SCFT correspondence. It suggests, roughly, that everything happening inside a volume of space-time can be described by physics happening on the boundary of that space in one fewer dimension, like a 3D image stored on a 2D holographic plate.
Whoa. So, Our 3D universe could be a projection from a 2D surface.
In a very abstract mathematical sense, perhaps. Applied to black holes, it suggests all the information about what falls in might actually be stored, somehow, on the 2D surface of the event horizon.
Stored on the boundary.
Yes, which could potentially solve the information paradox. The information isn't lost inside, it's encoded on the surface.
That is profoundly weird. It messes with your whole idea of space and where information lives.
It absolutely does. It suggests dimensionality might not be as fundamental as we think. It's a radical idea, still being explored, but it shows how black holes force us to confront these deep questions about reality.
Okay, mind officially bent. But this isn't all just theory, right? We have actually found these things. What's the proof?
Oh, definitely. The evidence has become incredibly strong, especially recently. For decades, the evidence was indirect, seeing stars orbiting something invisible but incredibly massive.
Like at the center of our galaxy.
Exactly. Sagittarius A. We've tracked stars whipping around it at huge speeds. The only explanation that fits is a supermassive black hole, about 4 million times the sun's mass.
Just watching stars dance around nothingness?
Pretty much. But then came the breakthroughs. 2015, LIGO.
Gravitational waves, I remember that. Huge news.
Monumental. They detected the faint ripples in space-time itself, caused by two stellar mass black holes spiraling into each other and merging hundreds of millions of light years away.
Directly hearing black holes collide.
Directly feeling space-time shake from the collision. It was the first direct detection and a stunning confirmation of Einstein's predictions. And LIGO and other detectors have found many more since then.
Okay, so we've heard them. Have we seen them? Sort of.
Sort of is the right word. In 2019, another huge achievement, the Event Horizon Telescope, or EHT.
That famous picture.
That iconic image, yes. It wasn't a picture of the black hole itself. You can't photograph something light can't escape from, but it was an image of its shadow.
The silhouette.
Exactly. The dark region of the event horizon silhouetted against the bright glowing accretion disk of superheated gas swirling around the supermassive black hole in the galaxy M87.
Seeing the edge of the abyss.
A perfect description. It was incredible visual proof, matching the predictions of general relativity for what a black hole should look like remarkably well.
So we've seen stars orbit them, we've heard them merge, and we've seen their shadow. The evidence seems pretty solid now.
It really is. Black holes have gone from purely theoretical curiosities to observed astrophysical objects, and they really are cosmic laboratories.
Laboratories for extreme physics.
The most extreme. They push gravity and quantum mechanics to their limits, forcing us to confront how those theories might eventually unite. They challenge everything we think we know about space, time, matter, information.
It really feels like we're still just scratching the surface, despite the progress.
Oh, absolutely. Every gravitational wave detection, every new image or observation from telescopes like the EHT gives us more data, refining our models, sometimes raising new questions. We're constantly getting closer to understanding these enigmas.
And understanding them isn't just about the black holes themselves, is it? It connects to bigger things.
Definitely. Studying them tells us about how stars die, how galaxies form and evolve, maybe even about dark matter and the very beginning of the universe with primordial black holes. It's all interconnected.
What a journey from 18th century ideas to actual images and gravitational wave signals. It's quite a story.
It truly is. Science in action, tackling some of the deepest mysteries out there.
Okay, this has been incredibly insightful, really gets you thinking. And maybe here's a final thought for you, the listener, to chew on. This holographic principle idea, this notion that maybe, just maybe, our familiar three-dimensional reality could fundamentally be encoded on some distant two-dimensional boundary, like information on a black hole's event horizon.
It's a perspective shift.
It really is. How does that change how you think about the space you live in? About information, about reality itself? It kind of pushes you to question the very fabric of existence. Definitely something to ponder.